for Subir's last lecture of this school, and it starts with the topic on here. So here's the Subir.
Thank you. Okay, all right. So I got, yeah, my mic's working, yeah. So I got quite a few questions on this whole ancilla framework. So I thought I would actually work through the connection to the it's good to do a calculation from scratch. All right. So it's, it's very much in the spirit of mapping, say, the Anderson model to the Kondo model, or mapping the Hubbard model to the super exchange model. And in all of these cases, you can do it for the lattice, but to leading order, you just need one or two sites, and then everything is good. At higher order, of course, you have to start, the lattice becomes different from the, but let's just do it to leading order. So I just have the three layer. Right. And I'm just going to take free electrons. So my Hamiltonian, H ancilla, is some chemical potential, C dagger alpha, C alpha, plus J perp S1 dot S2, plus J condo, which will be S1 dot C dagger alpha, sigma alpha beta, C beta. Okay, my Hamiltonian. How many states do I have? I have 4 states of these sites. 4 times 2 times 2, 16. You can actually, using various conservation laws, you can diagonalize the whole thing. But we're interested in the low energy states when J perp is large. Okay, so when J perp is large, the spins will just form a singlet. And this will have energy minus 3 J perp over 4. And if I think of JK small, then this has 4 states, basically. It has the empty state, the C dagger down state, and it has the both occupied state. Okay, so call them 1, 2. These are the 4 states. Okay, what are the energies? Well, to leading order, the energy is just given by the chemical potential. So to leading order, you would say that, first of all, E0 is minus 3 J perp over 4. E1, which is going to be equal to E2 always by spin rotation invariance, would be minus mu, no, minus 3 J perp over 4 minus mu. And E4, well, sorry, E1, 2, 3. And E4 is minus 3 J perp over 4 minus 2 mu. So this is in the limit that JK is 0. Okay, so now let's do perturbation theory in JK. So what is JK going to do? JK is the operator S1, and the operator S1 hits the singlet, it excites it to the triplet. Okay, so that's going to have energy J perp over 4. And if you just do second order perturbation theory, you have to come back to the ground state. And you'll see that, in fact, you're going to excite the triplet only if this is non-zero. And this is non-zero only for these states. These are spin up and spin down. This is spin 0. So it won't do anything. But next order, this is in fact exact. This is also exact. It doesn't change because it's a spin 0 state here. And this becomes, if you work it out, minus 3 J perp squared over 16, no, J perp. Okay, and then this has corrections. In fact, you know the exact answer, but it's only consistent to work to this order. It's only consistent to work to this order without if you had a multi-site problem. Because at the same order, higher order, you'll start getting couplings between the sites too. But to this order, you don't have to worry about it. And this, okay, so these are the energy levels that are of this three-site problem. And what that the same energy levels of Hubbard model which I'm going to say is minus mu prime, C dagger alpha, C alpha, plus U n up and down. So you, of course, know the energy levels of this Hamiltonian. It's basically number of particles times mu prime plus U only for the W occupied site. So you take those energy levels and you match it to these, and perfect match, provided you choose, U turns out to be 3 JK squared over J perp, and mu prime turns out to be mu plus, 8, 3 JK squared over 16 J. Okay, so answer, and of course there are corrections here. So this is at the order, this is an exact mapping of low energy Hilbert space of the three-layer model to the Hubbard. So this is what I meant by Stifel transformation. So the canonical transformation here. So the point is in this model, spins are always locked in singlet. So you can map this model to that model by canonical transformation. In the new model, there's coupling between the Hubbard model and the spin. They're just in a singlet. So canonical transformation you have to undo if you will go results from this model to this model and you want to know something about the wave function of the Hubbard model. Okay. All right. So now let's get back, just finish up a few details of things I wanted to cover. So you just do that on the lattice, and you get this three-layer model over here with exchange JK, exchange J perp, and we've also put it in exchange J in the bottom layer. Okay. Then you take these two spins and you write it in terms of spin-ons, F1 and F2, F1 and F. Plug it into the Hamiltonian. That's the Hamiltonian. It's got these exchange couplings. These are free electrons now, so everything is an exchange coupling. You just do the parton decomposition, and then you just go ahead and factorize in Hartree-Fock and BCS channels, everything in sight. That's all I'm doing. Everything is then reduced to some mean field Hamiltonian of fermions. Of course, there's the important part, and where you have to put some thought. It's all about the symmetries in the gauge invariance. So you have to understand how the projective symmetries act on the bottom layer and how that affects everything. And straightening all of that out, if you do it the wrong way, you can get completely messed up, but I think I've presented the simplest way to do it. All right, so now what do we get from here? So let's see what is next. Yeah, so this energy function for the bosons, I don't think I showed it to you explicitly. I think I only showed this term I wrote on the board 2 lectures ago. And there's some higher order terms that you need to stabilize the state. So in fact, if you take the boson energy, this is purely phenomenological, this you just by symmetry and nothing else, you have all these couplings that you just free to choose. And we choose all of these couplings so that somewhere in the phase diagram, so we can get D-wave superconductors, charge density waves, probably even pair density waves and all of that in mean field theory. And so we're going to work with, I'll just show you results, for the case where the ground state is a D-wave superconductor, plain old D-wave superconductor with no translational symmetry breaking, but the next best state is a period 4 stripe. And you'll see in some pictures where that's important. Okay, so now let's just think about the onset of D-wave superconductivity in this model. So here's, the model is here. So this phi is the hybridization in the top two layers. That gives you the pseudo gap. And B condenses at 0 temperature. So B is just a number. And we choose B to make the system a D-wave superconductor. So what you see here, there's some pairing terms here. And that's what induces superconductivity. From here, it feeds onto the top layers by some into the C because they're all hybridized with each other. Okay, that's really all you're doing now. You just condense B, and then I'm going to show you some pictures of diagonalizing this 3-layer Hamiltonian. Yeah.
So again, is he like a parton of the C electrons, or is he a parton from? Are you allowing the insular layers to become doped?
So the B, as this picture shows, is the decoupling field from the J-perp interaction. And phi is the decoupling field from the Kondo interaction. So you have two exchange interaction, you decouple both, and they give you two different Higgs bosons. And now I'm just putting them both equal to a constant. That's all.
It's not charged.
It is actually charged. So what happens is that when you condense the Higgs boson phi, then this layer gets charged because in the Kondo lattice, the spin-ons are charged. And then when you condense B, that also, B has an index associated with this one, it also acquires a charge. When phi is uncondensed, well, then becomes things big, and I haven't talked about that. You have some other gauge fields to worry about. On the other hand, when phi is uncondensed, you get a Fermi liquid. So what you want is the gauge fields, whatever they are, to drive confinement into forming singlets in the bottom two layers. And that turns out to be a little tricky in this formalism. Yeah.
So how much of these results, if you went back and looked at old literature of two-channel Kondo lattices, could you see?
This is not a two-channel Kondo lattice. There's really no, there's some passing resemblance to two impurity Kondo model. There's two impurities, S1, S2, coupled to a conduction electron. But it's coupled in a very particular way. Only one of them is coupled, not the other one. You can also couple the other one, but weaker. But really the key, all of the physics, really, all the phases I'm talking about come from spin liquid in this direction. They come from this spin liquid. And that physics is entirely missing from any impurity Kondo model. Yeah. Which one? Yeah, so, you can see it from here. So first of all, for now, imagine phi is condensed. Then F1 is just, F1 is in the middle layer, is just like an electron because it's hybridized with it. So when you now decouple S1 dot S2, you get this coupling here. And now you can see what kind of charges B carries. So now F1 carries the electric charge and physical spin. So but the physical spin is zeroed out here. So the B is spinless, but it carries physical charge E. Then on the other hand, F carries an SU2 gauge charge of the gauge field U. So B also carries the same SU2 gauge charge for this thing to be gauge invariant. So the nodes have a very systematic way of long listing of all the symmetries. And that's really the key thing to everything, understanding the symmetries. Yeah. So when B is not condensed, then U is fluctuating, and even at finite temperature. If U confines when B is not condensed, then you will just get Néel order or VBS order from this theory. So, all right, so when B condenses, then everything is Higgs, then everything is fine. Yeah.
They're not like a coupling between the S1 spins as well.
You can put it in, but it's that coupling that led to this hopping here. That's also Hubbard-Turnovich of that. So we did that earlier. That's the condo lattice part. So in the condo lattice, there's coupling between the S1 spins that you decouple that, and that's how you get the hopping of the F1s. Yeah. So if there is a map at next order, there's a mapping here. Then in the end, when you do the canonical transformation, you will get additional exchange interactions here. So you'll get some kind of with additional couplings. So TUJ model. Yeah.
No question. So if I have a very small condo problem between C and S2,
Yeah.
it's stable against small thing.
Yeah. So yeah, let me just, I think this will answer it. So if you think in terms of condo physics, S1 has an antiferromagnetic coupling to the environment, to the conduction electrons. S2 has a ferromagnetic coupling because this is antiferro, so the effective coupling is ferro. So these spins have a ferromagnetic counter coupling, so they just flow to, the ferromagnetic coupling flows to zero. So these spins become free as far as the top two layers are concerned. So what they're going to do is form singlets within themselves because they're ferromagnetically coupled. This one is strongly coupled, this is strongly relevant, so they'll form a condo lattice. All right, wonderful. Okay, so I just go ahead and condense B, and then all right, so let me show you some pictures of just diagonalizing the top three lines here. Okay, so when B is 0, then I have two decoupled systems. I have the condo lattice on the top layer, and that gives me this Fermi surface. And then I have the spin-ons of the bottom layer, and these are the 4 spin-ons of the bottom layer. So this is the FL star state, which is the 0th order starting point for describing the pseudogap. What I showed very briefly at the end of my last lecture is when you put in thermal fluctuations of B and U, they kind of remove the backside because the spin-on couples to the backside through the fluctuations of B, and then they kind of annihilate each other, at least thermally. Okay. All right, so now how is this FL star state going to become a superconductor? So there have been many things in the literature where people just, through some approximation or the other, some DMFT-like theory, they get these pockets. And then you ask, let's make this a superconductor. How are you going to make a superconductor? You have this strong tendency to say, well, just pair the Fermi surface. All right, so now if I pair the Fermi surface, what happens? Suppose I have D-wave pairing, which is what you would get in many calculations. And so now this is where the gap vanishes. The gap delta K vanishes along these dashed red lines, there and there. And therefore, since these are pockets in simplest theory, I have 8 nodal points. The red dots are the nodal points of the D-wave superconductor. And I also have 4 spin-ons. Now, so photo emission, this is not such a problem for photo emission. You could say, well, first of all, the spin-ons don't contribute to photo emission. And the backside has very low intensity, so let's not worry about this. However, for thermal conductivity, this is a huge problem. So for thermal conductivity, all of these nodes, all of these dots, the red and the pink, are going to give you thermal conductivity of 12 Dirac nodes. Now, thermal conductivity is something you measure very accurately. And it's very clear from various experiments that there's only 4 nodes. There's no 12 nodes. So this doesn't work. So if you apply the BCS pairing mechanism to the pseudogap, you do not get the right D-wave superconductor. Another way to see this, and this is a state that we call DSC star, meaning it's a fractionalized state. This is a state with spin-ons. Now, if the spin-ons was really there, it is not smoothly connected to any large Fermi surface D-wave superconductor. It's some exotic superconductor. And somebody saw this, well, that would be fantastic, but there's absolutely no sign of it. Yeah.
Would this also be a problem for if you were claiming that the backside was removed just by antiferrometric fluctuations? Now I get 8, and that's still not 4?
Well, I mean, the point is that now we are at 0 temperature, so all of those, the antiferromagnetic fluctuation.
Due to conventional antiferromagnetic fluctuation. You already said that
Okay.
it doesn't get the count right.
Yeah.
Would it also be wrong because it would get the wrong number of?
Well, yeah, so you're saying, suppose I had a fluctuating spin density wave theory coexisting with the D-wave superconductor.
Yeah.
Yeah, if such a thing is possible, but it would have 8 nodes then.
Okay.
Yeah. All right, so that's not right. What you have to do is, this is the rough idea of Anderson's 87 paper. The spin liquid already has a pairing in it. You got to use that. And that's exactly what condensing B does. What you have to do is condense B. So this is an artifact of the particular gauge I'm working in. Here the pairing is in the Yukawa coupling, but you can remove it and put it in here, in some other gauge of the SU2. So there's a pairing in the spin liquid. All you got to do is hybridize the spin liquid with the Fermi surface, and you get a superconductor. Okay. So here in this language just means you have to condense B, and depending on which gauge you're using, you'll have different components of B. That's the tricky part that you have to very carefully work out. All right. So when we condense B, everything mixes with everything. Okay, they're all electrons because people make. So what's going to happen is that these 2 nodes are going to annihilate, yes, annihilate with each other.
This calculation self-consistent?
Yes, I mean, we haven't done it, but in principle, yes, it's a lot of work, but I see no, I have to ask Maine. I think she may have done some instances fully self-consistently.
Okay.
I don't remember for sure.
Okay.
But, yeah. But I mean,
like
Well-
you plug in some value for the B order parameter, and is it consistent?
well, so maybe let me say that again. So if I go back here, so, the phi is obtained by decoupling JK, and the B is obtained by decoupling J perp. So there's a self-consistency equation in the Hartree-Fock procedure, which relates B to some expectation value times J perp, and similarly relates T1
You mean like a
phi
gap
to,
equation?
huh?
Like a gap equation for these?
Yeah, so there's about 3 or 4 gap equations here, which is a huge pain in the neck to solve, but yes. I think Maine have done some simple cases, I don't remember. Yeah. Everything is pretty really, yeah. Just get qualitative with the right phase. And even that has not been accomplished. So, yeah, this is ultimately, okay, so actually that's a good question. So for example, the T1 and the phi, we are completely fixed by matching to photo emission. That's what we did. So when I'm drawing this picture here, that's fixed, completely fixed T1 and phi. Okay, so the only thing that's not fixed now is B. Yeah, so I'm just treating B as some, there's really only one free parameter. I was joking, yes. Well, okay, there is this J here, which is the spin-on dispersion, but I'm hoping that fairly soon we'll be able to pin that by actually measuring the spin-ons and neutron scattering. There is the J here, and that will have to fit to neutron scattering. I mean, everybody fits the hopping matrix elements, Yeah.
No.
It is closed from the top 2 layers, yeah.
Go to the next slide. This pocket is like the back is not that bright, but
So this is for the, so I'm just computing the spectral weight of the CL physical electrons. And so it is smaller. So if you did photo emission, this is the intensity you would see in photo emission. That's what the curve is plotting. So the intensity of the back is very, just by diagonalizing the matrix and putting in all the matrix elements, you get a suppression at the back. That's very natural in so many theories. What I showed very quickly at the end today was how gauge fluctuation would make it even fainter in the normal state. Yeah.
I see that on the Fermi surface chart not exactly look like this. And last time when you were comparing the result with magnetic transport, you were saying, okay, we are assuming it is. Want to ask how much gauge does it?
Paper is coming soon on that question. So yeah, I forget. Maybe he's, I should know his name. One of Yahoo's postdocs is doing exactly that calculations. Yeah.
If you go beyond the SYK and with gauge fluctuations,
Yeah.
is condensing these somehow you go to quenches that those gauge codes?
Yes. Yeah. So that's the other advantage of condensing B. All the gauge fields are gone, or Higgs. So then you're pretty confident this is just an ordinary BCS superconductor. Yeah. So you really need to, if you're going to think of the pseudo gap as a spin liquid phase, there's no choice but to have a confinement transition to the superconductor, unless the superconductor is very exotic, which today, there's really no sign of that. Yeah.
Backside of the pocket.
Yeah.
So is it just the quasi-particle residue that's getting very?
Yes.
And so if I look at deeper energy, all that weight sort of comes back. I could look there and have more spectral weight, or
Okay. Well, so this picture is only supposed to be there at high temperatures in the pseudo gap regime. At low temperature, you can find either into this D wave superconductor or into some charge density wave state. And then it just basically goes away. There are some high energy stuff on the backside, you're right, which we have in our papers, the band structure of that. And yeah, it would be great to look for. Well, I mean, this is coming by some hybridization between the physical Fermi surface and another Fermi surface. Yeah, but there are some higher energy bands over here in the superconducting state. So once I go superconducting, then the nodes are removed completely. And there you go. And now I got a D wave superconductor. And yeah, the backside is basically gone. This is just a picture where I have, it's a picture in the normal state, but there is no backside. We have in our paper, the second paper here with Main, all kinds of spectra at high energies on the backside. Yeah, it would be great to look for that. Yeah, that would be a real acid test. It's complicated, but it's not at zero energy. Yeah. Okay, so this is the reason for showing this, is that now you immediately see, you solve the biggest problem with the spin liquid theory from the early days, from the 90s, that it gave the two velocities, this velocity V delta and velocity VF in the D wave superconductor, they were equal to each other. But now we see they actually can be very, very different because they're determined by totally different things. VF here, so this is, VF is determined by the Fermi surface, so it's fully determined, as before by the hopping in the top layer. Whoops. So it's determined by these hopping. Okay, so it's as you would, it is coming from the remnant of the large Fermi surface. So that gives you a large VF. And on the other hand, V delta is determined by the B condensate. It requires pairing to have so there was no pairing there. And, so the key point is that the spin-ons, in the old theory, the spin-ons, the pink dot became the nodal quasi-particles of the superconductor. And that led to all the problems. What's happening here is that the pink dot actually is, is like the janitor. It just sweeps away the unwanted, the unwanted nodal points. And then you're left with the other nodal point that came from the Fermi surface of the pseudogap phase, a Fermi arc. The nodal points come from the Fermi arc, not from the spin-ons, which is also what you see. It's the Fermi arcs that become the nodal points. Yeah.
So what says here the energy scale of the gap at zero temperature?
Well, everything is J, I suppose. Yeah, but yeah, but we don't have any quantitative handle on that. Yeah, yeah. It's the size of the B, it's the square of the B condensate. Yeah.
Like this momentum derivative of quasi-particle energy.
Well, so so once you have a superconductor, and then near this point, if this is k equals 0, and let's call this x, and let's call that y, then the dispersion ek is square root of vf squared ky squared plus v delta squared kx squared. So this is just what happens in our BCS theory also. This is what the actual dispersion of the super Bogoliubov quasiparticles, and this defines VF and V delta. So that's only in the B condensed state. So you shouldn't be looking at the, I should draw, yeah, I don't know, okay. The picture is of the dispersion in the normal state. And I've just sketched by hand in PowerPoint all the red stuff. Okay. Yeah. Well, I think, like as I discussed, it's totally fixed by the magnitude of B. So like, so there is, in the end, no free parameters left because we fixed all of these by matching to photo emission. Let's say we fix this using neutron scattering, or you can just fix it in the insulator where you know the spin wave velocity and some theory that converts the spin wave velocity in one phase to the. So within 20–30%, so we don't have any issues there. And then maybe we can fix B by V delta, and then we're done. There's no free parameters left.
What was the issue there with fixing VF of V delta?
So so they didn't have all these multiple layers. They did the slave particle description where they wrote down. They just had one layer. They just said C alpha was some boson F alpha. Let's say, oh well, dagger. You had a spin liquid where you had F alpha non-zero. This was your spin liquid. And then in the spin liquid, you just condensed B that carried all the density. And so the superconducting pairing was just B squared. And the dispersion of the quasiparticles, at least a small delta, was entirely given by the dispersion of the spin-on, because this is just a constant. And so VF and V delta were the same. Yeah.
Is it just because we only had a Dirac node in the normal state, not this arc? So
Correct.
The same velocity, not.
That's right. So they were going from a spin liquid to a superconductor. I'm going from a pseudogap metal to a superconductor. Yeah.
Banded Hubbard model.
So, yeah, you mean this 3-layer model? Yeah. So in the 3-layer model, this boson B in the old days is the analog of the Hubbard-Stanovich coupling of J perp. It has the same quantum numbers. That's all. Yeah, no. Well, that's why we're going through. If you could just get everything from the extended Hubbard model, then why bother with all the song and dance I've been presenting? Yeah, that is the whole purpose, because you can't get it from the extended Hubbard model easily. Certainly, you can do some very uncontrolled, well, not some beautiful DMFT type calculations with big computers, or you could write down these strong coupling dimer models that I wrote down yesterday and wave your hands a lot about how bound states form. And that also required computer calculation at finite density. This is, if you want to get everything in the mean field theory, this is it. Yes.
So the spin-on Fermi surface, when you condense beads.
There was no spin-on from it, the nodal points, it's a Dirac spin-on.
Point to Dirac.
Yeah, absolutely. The Dirac spin-on is
VF
essential.
is the VF of the Dirac.
Yes, no, V delta, the spin-on is gone. So this is,
Can you give the normal state?
this is the normal state, where these are the Dirac spin-ons. And then you have this Kondo lattice, which gives you the pockets. Okay. So remember my slogan, pseudo-gap metal equals Kondo lattice plus spin liquid. The Kondo lattice gives you the yellow, the spin liquid gives you the purple. And the calculations we've been doing for the last 2 or 3 years, we're really using the Dirac nature to get all this to work. Otherwise, it doesn't work.
I think you still the pink nodes, but you open up nodes on the.
No, so when you go when you go superconducting, initially, this is, so just close to TC, at least in mean field theory, you still have 12 nodes. This is a superconductor now with 12 nodes. You've killed the yellow. Maybe I should draw a picture where the yellow is not there. Ignore the yellow. The yellow is gone. You only have now 12 nodes. But the only way Dirac nodes disappear is by annihilating with each other. They just can't go into nothing. So that's why you need the Dirac nodes. Otherwise, you'll run into trouble. But now, calculations show they do indeed annihilate, and then you're done. Yeah.
If I'll start, what's the parameter that puts the spin-on node near the backside of the Fermi surface?
Well, the spin-on node you can move it around it's a gauge choice, but okay. So the spin-on node is a pi by 2, pi by 2. Question really is what puts the Fermi surface near the spin-on node, right? That's energetics. We are just going from experiments, trying to get the arc. It is away from. It's exactly where this is. The spin-on has to be at pi by 2, period. And we are just using an experimental fact that the arcs look like this, very close to the zone boundary.
But there's some theory that tunes Higgs transition of the B, and parametric in the distance to that transition.
Yeah.
Must get close to the Fermi surface. Is that correct?
Well, yeah. So right. So when B is infinitesimal, they don't quite annihilate. And as you increase B, eventually they do annihilate. Yeah. Yeah.
Passes DFT
Sure.
there.
Well, so the DFT calculations have all the arcs and everything. DFT or DMFT? No. DFT gives you a big Fermi surface. Yeah, but then it doesn't have a pseudo gap. So DFT, forget it. It doesn't work at low doping. Of course, it is roughly where the front part is, but it's got a lot of other stuff that you don't see in the antinodes. Yeah, no. DFT is a non-starter. DMFT is fine. They do, in fact, get these kind of things. They don't have resolution to really see this smaller pocket, but okay, I'll grant them you see it. But what they don't have is the spin-ons. And if you're missing the spin-ons, it doesn't work. You get the wrong type of superconductor and so on. Yeah.
Yesterday, the artist that you showed, the old shed work, the antinodal modes that you saw, with a gap.
Yeah.
What's that in the theory?
Oh, that's still here. I mean, they're gapped, and the condensing of B will change them a little bit. But that's still present. I mean, from the top 2 pairs in the antinodal region. Where is it? Sorry. Yeah, so it's this part of the Hamiltonian with the phi, this phi here, which determines, where did I show that? Yeah, here. So that phi determines this gap from the Fermi surface. I don't know why these units are so strange, but anyway. Yeah, no, there's a gap here, and that gap's supposed to map onto this gap here. And that's how we fit the value of phi. And that's still there. Now, will we also get that green part? I think we will, but we haven't looked for it carefully. So there's two gaps near the antinode. There's a gap due to B and there's a gap due to phi. Near the node, the gap is entirely due to B.
Right, in the experiment, the green bit is in the superconductor.
Correct. Yeah. No, but the blue bit is still there too, I think.
Right.
Yeah. It may move a little bit, but it's there. I can ask Dan, he can answer this. You remember all this picture? So the blue bit is supposed to be the pseudo gap at low temperature. I mean, and then in the superconductor, you get another shoulder at the green. But is this peak at blue still present in the superconductor?
Yeah, it's far enough away from.
Yeah. Yeah. Right. That's what I've done. So that's exactly what happens in this theory too.
So I guess once you open a small gap, that green should be parametrically close to the thermostat.
Yeah. So this is right.
Yeah, everything's fine.
Right. I mean, you're deep in the superconducting phase here. This is a very good superconductor. Or I don't know, 2201. I don't know what doping this is. What is TC here? It's not that low. Anyway, it's slightly overdoped maybe. Yeah. Oh, slightly underdoped. Yeah, sorry. This is definitely underdoped though.
Same energy as the
You mean the green and the minimum of this? Yeah, I don't know. I mean, what people normally call the pseudo gap is actually this. It's only when you carefully look in photomation that what you call the pseudo gap disperses. This is one of the first papers to point that out, right? Okay, Dan can correct me. Of course, but I talked a lot about that yesterday, how those inputs can all have trouble with the recent magnetotransport experiments, except the spin liquid description. All right, I shouldn't be so confident, but. All right, I think that was what I wanted. Well, I'm going backwards, sorry. So now I've described the superconductor. Let me just flap, a few pictures. So what we've done in our paper from last week is we did a Monte Carlo simulation of this theory where B is fluctuating. And so this theory undergoes a costless, Thouless transition. And this is well below, this is deep in the superconducting state at very low temperatures. And this is the phase of the superconducting autoparameter. So you see that there's all these points where you have phase winding by 2 pi. So that's very reassuring. You know, the B is charge E, but the phase winding is of a charge 2e autoparameter. So each of these vortices here will carry flux h over 2e. And how does that happen? Well, that happens because of the SU2 gauge field. SU2 gauge field is confining the B's together. And so that's included in our theory. And so the vortices here have flux h over 2e, not h over e. And that, you know, we're very happy to see that. That's what came out of the simulation. Yeah.
Sorry. Reaching the B's classically is
Yes.
justified in the limit where your temperature is much above some characteristic energy scale associated with the spin liquid. Is that right?
No. The B's are condensing. So near TC, it's exact. I'm just doing the static properties here. I'm not doing the dynamics of the, and they've got some kind of thermal overdamped dynamics. Yes. Well, the lattice, well, okay, that's a bit adjustable, but so this is the phase plot, and I think this is about, I think 100 by 100 roughly. Yes. These are vortices and anti-vortices, as you can see, they have to be paired up. And now, if you look at the bond variables, the bond density, which is like the SI.SJ expectation value on nearest neighbor sites, what you see are these modulations. So if I zoom into one vortex, this is what it looks like. And this is a modulation in the density. This is coming at period 4, and it's period 4, you can see that. It's coming because we chose parameters, so the next best state is a period 4 stripe. So at the core of the vortex, when the D wave goes away, you get the charge density wave appearing, or I mean, you have enough parameters, you get almost anything you want, but it's completely natural. There's no way to avoid something else appearing, which is the difference from Landau theory. In Landau theory, you can certainly have a set of parameters when nothing appears. Here, that's not possible. It's demanded by the pi flux that these bosons feel. And, that's, of course, looking strikingly like, so we're very excited by that, by these STM data from a long time ago.
Here, the vortices are much, much longer, larger than the ones in your calculation, right?
This is literally one lattice spacing here. So there's 4 lattice spacings right there. Yeah.
What's the 100 angstrom?
Oh, that much is 100 angstroms. Let me see. Yeah, from here to here is about 4 lattice spacings. Yeah, I think that's about right. Well, a 4-unit cell periodic pattern of, you can see in the title. Okay, I mean, we didn't adjust anything, I mean, other than just every vortex. And the point is, it appears in every vortex. There's nothing that doesn't have it. This theory, the only thing that determines is the size of the Fermi surface. So the doping has kind of, this is a theory only for the underdoped. So of course we know experimentally the underdoped side, you don't see this. Overdoped side. So there's all these parameters here, and so it's the usual, well, you have all these parameters, and you can adjust them to get things incommensurate, commensurate, and so on. These are quartic terms in the B Landau expansion. But the point is that it's the quartic terms, and the quadratic terms really impose the fact there's always a secondary order parameter on the underdoped side inside of vortex core. All right, how am I doing on time? Okay. All right, so now, yes. Yeah.
I think I understand. So if there's a parameter that one can tune that would justify diffusion with these plus. Could you say again exactly what that is?
Well, it's simply the statement that near a classical thermal phase transition, near TC, you can ignore quantum mechanics. And the transition is a transition of this, this SU2 gauge theory. And you can also forget about the fermions. Fermions renormalize various couplings, and they're not important. And so we just do classical Monte Carlo. It's completely the analog of the phase fluctuation calculations that were done earlier, where well, it's a simpler version. No, it is the analog. So you just take a classical XY model to describe TC, and then you take the snapshots of the XY model to diagonalize the fermion spectrum.
That's a big critical regime in temperature.
Well, I mean, then once I go into superconductivity, I'm only describing the condensate, yes. So there may be some, eventually at 0 temperature, near a superconductor insulated transition or something, I will have to worry about quantum fluctuations of B. I describe the FO star, the fermionic part, I describe exactly. I don't use classical theory for the fermions. There's the thermal fluctuations of the bosons. Yes, I use classical fluctuations.
Treat them as just thermal fluctuations. You need to be parametrically close to TC.
Strictly speaking, yes. Right.
So,
fine. Yeah, no, I think, okay, fine. I mean, so in our paper, we have a calculation where we do better, but only perturbatively. We put in quantum fluctuation with the bosons, you don't get a very different result. Yeah, I mean, the point is the moment you put in quantum fluctuation to B, you have a sign problem. So I don't know how to do better.
Had to describing things using thermally fluctuating superconductors, vanilla superconductors. Was that have a big
well, the objection there was that the fermions were incorrect. That, I had no objection to using the thermal fluctuation, the superconducting order parameter. The objection there was you were using thermal fluctuations of the superconducting order parameter to get a pseudo gap in the antinode. That's incorrect. Here, I'm not using thermal fluctuation to get a pseudo gap. I have quantum theory of that. So roughly speaking, near the node, I can use thermal fluctuations of either gauge theory or an XY model, but near the antinode, it has to be fully quantum theory. And that distinction is not made in the old theory. You really need, it's very clear from, this data that we were saying. The pseudo gap has nothing to do with the pairing gap. I think a lot of that's, Kibbleson's on this paper, so I'm sure he will agree with me. Well, I don't know. No, I've discussed this all with him great length.
I agree.
Okay, fine. Where is it? This paper, this paper here, I think he's on the author. Yes, everyone's on this paper. This is a very nice paper which shows there's no connection between the pseudo gap and the superconductivity. Yeah.
The role of the reading.
And this is much later than the old phase fluctuation papers. It's only 20 years ago. Yeah.
I missed the role of treating the Hubbard-Strange field in, adding the thermal factor. If you already have the gap, why do you need to treat this B, for example?
Yeah. So for the antinode, I don't need any of this. No, this is all for now understanding the vortices or understanding what happens near the nodes. I do need the thermal fluctuations. Yeah. But for the antinodes, this old theory in this paper is perfectly fine.
But these are some bosonic fields. So what phase are those bosonic fields in? Do they have long range order at finite temperature?
No, these are all Higgs fields. They don't by themselves break any symmetries. So they all carry gate charges. I've put a few of the gate charges under the rug here. What you have to do whenever you have Higgs fields, the rule is the following. You take your Higgs fields, some of them may be condensed and some of them may not be condensed. You take the condensed Higgs fields and you try to form gauge invariant operators from the condensate. Look at all possible gauge invariant operators you can form from the condensate. If those gauge invariant operators break a symmetry, then a symmetry is broken. If they don't, nothing is broken. So that's exactly how we get superconductivity here. The gauge invariant operator that you can make out of B has charge 2e. and so because it has charge 2e, it's condensed, and so we have a superconductor, which has broken a global U1 symmetry of charge with charge 2e, and so on. With the charge, to see the charge density wave, it's not enough to have a condensate that's modulated. What you need is a gauge invariant, SU2 gauge invariant. That's an even stronger constraint. Combination, SU2.
What's the other field?
And B also give you CDW, depending on the orientation of B. It's got two complex components and arbitrary spatial components. So there's a lot of parameter space to investigate. Yeah, sure. Well, the last talk, anyway, okay.
Conducting though.
Yeah.
The B, the Higgsing of the B is getting weaker and weaker, right?
The left end. Okay. I was going to show the superconducting dome anyway. Yeah, there we go. No, that comes a bit later. All right. Yeah, so you're talking about Rome P min here?
Yeah.
Okay. Right, so this is, who knows? Here there's localization due to disorder. There's a transition to magnetic order. I'm certainly not trying to describe that. But there, absolutely, I agree with you completely. Over here, I would have to include quantum fluctuations of B. You could not get a description of that transition without quantum fluctuations of B.
So I guess what I was about to say is that, the thing that Kibbleston did stress in
Yes.
this work was that in our pairs,
He was talking.
pairing gap stays big towards the left end of the door.
Okay. Well, I don't know. I don't know if he was going all the way down here, but you know.
I think he was talking towards the end of the dome.
But I think it wasn't it here.
Yeah, but both ends.
Okay. Yeah, all right. I would say our theory can't describe that very easily then. Yeah, at least not the main field theory. Okay, great. All right, so my original plan was to make this lecture about the strange metal. And also maybe since we heard from Dan yesterday about these, you know, strange non-Fermi liquid-light behavior extending over a big regime rather than just at a point at low temperatures. So that's sometimes called the foot. All right, so that's where I wanted to go. So let's see. Well, let me just go according to plan and I'll stop at some point at the right time, 10:30, right? Okay, so what we want to describe, first of all, let me just say a few things about the SYK model. It's an artificial toy model, but as you know, many toy models teach us a lot. And I think this has too. Perhaps it's taught more to people in quantum gravity and structure of black holes, but I think it's also very useful in condensed matter, which was its original motivation. So basically, what you're looking for is some solvable model of interacting electrons, which does not have quasi-particle excitation. So, you know, and in fact, there is, if you think, you know, if you go to the Bethe-Ansatz soluble integrable models, they all have quasi-particles. There may be some exotic quasi-particles, fractionalized degrees of freedom or something. But there is some quasi-particle description of the low energy, of the entire spectrum, in fact, for the integrable system. So, and that's, you know, obviously, so there we don't even have an example of a quasi-particle. Sometimes people say Luttinger liquid is a non-Fermi liquid. Well, it depends what you mean. It's a non-Fermi liquid in the sense that the electron is not a quasi-particle, but it has free bosonic modes. In fact, this full spectrum is described by just free bosons. These bosons are some emergent particle. So, but as far as we know, in higher dimensions in the non-Fermi liquids, there is no hidden quasi-particle there. I mean, there could be, but as far as we know, there's nothing. So we want a model in which not just the electron, but there isn't any hidden quasi-particle excitation, out of which you can build the physical states. You know, there are Laughlin quasi-particle fractional quantum Hall state, there are spin-ons in at least these spin liquids. But the thought was that, you know, if you have a metallic system with strong interaction, the experiments seems to suggest very strongly that there are these states of matter, which are really new in the sense that there is no quasi-particle basis. Okay. So for a long time, I mean, maybe even some today are skeptical that such states even exist. Okay. Well, I'll show you a toy model anyway, where we can prove that such a state can exist. Yeah.
So is it in the same sense qualitatively as, you know, absence of quasi-particle point?
Yeah. So,
Same sense.
yes, so I should say that 3D Ising model, yeah, thank you for reminding me. We take the 2 plus 1D quantum Ising model at its critical point, which is the Wilson-Fisher point. That, still unproven, is expected to be a system that has no quasi-particle excitation. So it's really a conformal fixed point, which is far more complicated than, or chaotic is the word people use, than any conformal, well, at least large, all of the conformal field theories that we understand in 1 plus 1 dimension. Those are all much simpler. I mean, there are certain large central charge holographic theories that you only understand by gravity duals, but yeah.
Plus one, they do have quasi-particle.
Yes, yes. Yeah, all of the minimal models and so on. They're not chaotic. But there's large C conformal field theories are not really solvable except by some holographic mapping. Anyway, okay, so with that philosophical introduction, so let's just take, so it turns out the trick here was to first look at random systems. And in condensed matter, no, we are very familiar with the idea that randomness actually makes it simple. For particle physicists, that was a shocking idea, but now they seem to be doing it every day. So we just look at, first let's begin with the simplest, random matrix model. This is the matrix model of Wigner, which he introduced to describe nuclear energy levels. But now we think of it as some random hopping model, Tij, of fermions that are hopping on some n sites. So you can go from any site to any other site with some amplitude Tij. Okay, and that's it, free fermions. So let me just review this, what its properties are. So Tij, for simplicity, have zero mean and some root mean square value. And the most important thing is that they're independent random variables. The distribution actually doesn't matter much. Okay. All right, so how do you solve this? Well, of course, if you want to get the distribution of all the single particle energy levels and their spacing, then it's a complicated problem, but it's been solved and a lot of things are known. But if you just want the density of states in the single particle Green's function, it's very easy. You can do it in a few lines. Basically, you just do perturbation theory. So you have some G0, which is when T is equal to 0, which is just a I omega minus mu or plus mu delta ij. So it's just completely on site. And then you put in T. So here's T. So then you'll go from site I to site j, and so on. Okay. T, this will still be j, and then you go to some other site k, and so on. And now you just average. You perform this average on every term in every Feynman graph. And what you see is that if these were different sites, because they're uncorrelated, you'll get 0. So the only way you're going to get something non-zero is either the same site, if basically I is equal to k. So the way you draw that is you connect them up. So this means there's a factor of t squared that's going to come. You're taking the average. You put a t squared here, and then this becomes an I, because the different sites are uncorrelated. Okay, so that's it. That's the only graph that appears at second order, first order. So what's the value of this? It contributes a self-energy, which is t squared over times g. Okay. And then this is going from site I to I, so it's sigma I. And this is also GJJ here. And there's a sum over J. Okay, J can be anything. But there was a 1 over root n over there. So that gives you t squared over n. So the sum over J gives you n, that cancels that n. And it's just t squared times G. And G, we assume, is independent of I. So it's just G. You can drop the sigma. Independent of J, sorry. No, there's an arbitrary, there's a general frequency, there's a sigma of omega here and omega here. So that's what I wrote down here. So that's the term to second order. And now the point is that in the large n limit, this is exact. There's no corrections. So you could try to think of various corrections. For example, a term like this. So, these are the kind of terms that lead to weak localization and all of that. So, you just do the counting. If this side is I, this side this has to be I. If this is J, then this will be J here. And let's say this is K. Now J and K are, well, that doesn't work because, anyway. So that's I. This is also going to be I. And so then everything, yeah, something is going wrong here. So this is J, let's see, that's I. This has to be I. Seems like everything has to be I. Okay, I don't know. So this thing, it's got T squared and T squared over N here and over N here. So it's down by all these factors of N don't cancel with anything else. All right, so you just sit down and look at this at higher orders and you find there's nothing. You can also do this using path integrals and so on, but this is the simplest pedestrian way. All right, so now the nice thing is that in frequency space, all you have to do is solve a quadratic equation, which you can solve, and that's the quickest way to get the semicircle distribution. So a random matrix has a density of states, which is a semicircle. That's what you get by just solving this quadratic equation. So in the large N limit, there's a continuum of states. This is the density of states. Yeah, so but however, of course, at any finite N, there's a discrete set of energy levels. And the spacing between these levels is 1 over N, because there's N levels. This is all of order 1. So if you're fitting N levels in a window of order 1, their spacing is of order 1 over N. Now, what the Dyson theory of random matrix eigenvalues is that the spacing between these eigenvalues is almost constant. It fluctuates, but probability of fluctuations is suppressed. They don't really come very close to each other. And so there's some universal distribution of these fluctuations. I'm not interested in that. We're just looking at sort of gross properties here in the thermodynamic limit. So there's some density. So in the many-body system, there'll be a Fermi level. You'll fill up all the states here. And there's some density of states that you can compute from knowledge of the density from the semicircle. Gives you some rho 0. And then Sommerfeld tells you what the entropy is. Okay.
And infinity.
Right, yeah. So there's various tails over here. But the point is, for the many-body system, those Lifshitz tails are very far from this Fermi level. So those don't really affect the low temperature properties, even at finite N. I mean, a lot of people focus on that, but if you're thinking about a metal at finite density, they don't matter. All right, so now what I want to do is do something very silly, which is just take these single particle levels and think about the many-body levels. The reason I'm doing it is because once I have interactions, I don't have any single particle level. So I want to compare that. As condensed matter physicists, this is fine. We'll draw this and we'll go home. But let's just try to write it in a way that nuclear physicists, for example, might want to write it, because they're thinking of the whole nucleus. So what are the energy levels of the many-body system? Well, you have a binary variable. I'm working the grand canonical picture, n alpha for each energy level, and that can be 0 or 1. So there are n energy levels, so there's 2 to the n many-body levels. So I get 2 to the n many-body levels, which are, and their density of states I call capital D of E. Okay, so I know what I plotted before was the density of states of little e. Now I'm going to plot numerically. In fact, we still don't know today what the answer for this thing is. It's still a rather complicated thing, this D of E. But this is numeric, so here I don't know, it's a 16 by 16 sites and something, 2 to the 16th many-body levels. This is the density of states of the many-body levels. Okay, so what are some of the features of this that I want to highlight? So when the energy is extensive, when you're somewhere over here, when the number of particles is some finite fraction of the number of sites, and the number of sites going to infinity, then we can apply thermodynamics. Then Boltzmann tells us that the many-body density of states is the exponential of the entropy. Okay. All right. Now, what is the entropy at energy E? Well, what you're familiar with is this expression, but this is in the canonical ensemble. You just convert it to the microcanonical ensemble by Lagrange transform, and that turns out to be square root of E, n times square root of E. So you notice this is E is of order n, and so this whole thing is of order n. It's exponentially large in Avogadro's number. And that's right. So, and the number gamma here is the same as the gamma there. So if you numerically looked at this, it should fit at least to leading exponential, this form. And then you can ask, what are the corrections? Yeah, I don't think they've really been worked out. It's quite tricky. The other thing you notice is this tail. If you go right to the bottom of the band. So notice this is the bottom of the many-body band, not the bottom of the single-body band. The energy level becomes the density of states become very small. So here are the individual energy levels. They're exponentially dense once the energy becomes extensive, because the entropy is also extensive. But when you're at the bottom of the band, when the energy is about a 1 or about a 1 over n, the spacing is much larger. So the density of states here is about a e to the n. But the density of states at the bottom, in fact, is about an n on average. Now, how can I see that? Well, just go back to this picture here. So what are the very low energy many-body states? Well, there are going to be states where you take a particle from just below the Fermi level and excite it just above the Fermi level. And there's very few of those states. There's only energy level spacing is 1 over n. So in fact, 1 over n is a huge energy to pay in the many-body sense, because in the many-body thing, these energy levels are really, really close to each other. And the reason they're close to each other, is one level could be site 6, site 7, site 10, or energy eigenvalue 6, 7, 10 occupied. The other could be 2, 7, 2, 5, 9 occupied. And they're accidentally exponentially close to each other. They have to be, because there's no place for them to go. But at the bottom, there's very specific levels, and the energy level spacing is not exponentially large. It's just of order n, and this is very generic. And this is really a signal that these are free particles, okay, or the quasi-particle description. All right, so now we go to the SYK model. It's exactly the analog of this model, except there's no hopping now, but there's a random two-body interaction. All right. So now you can solve it by exactly the same tricks. You just write down graphs and take the large n limit. That's the simplest way to do it. Of course, there are many other fancy path integral methods which also allow you to do fluctuations. All right, so in this case, the analog of this equation, there's only one graph again, amazingly, that contributes. And it's this graph that now the string tier is called the melon graph. Okay. Anyway, so there's the melon graph, and that's it. If you do, for example, here's another graph, it's down by a factor of n, by the same trickery. Okay, so now you have a very similar equation to solve, except that for the random matrix model, you have sigma was t squared times g, and this could be either frequency or time. So let's make it in time. Whereas for the SYK, it's sigma of tau is u squared. I think there's a minus g squared of tau, g of minus tau. So now you have to just solve these three equations. There's a certain density Q, and these are the equations. All right, so I first wrote down these equations around 92 or something, And I thought, oh, someone must have solved these. This is so simple. It must be somewhere. And we know everything about it. It just must be trivial. Well, no, nobody solved it. And even today, we're learning new things about the structure of the solution of these equations. I think today they're very well understood. And there are connections to quantum gravity, all hiding in the solution of these simple equations. But they're not that simple because this is simple in frequency space, this is simple in time space, and so they're complicated integral differential equations that you have to solve. You can solve them numerically quite rapidly now on a computer. Okay, so what would we, let me see. Yeah, I should have another citation here. So what we understood already in 93 was that there's a square root of omega singularity. And then Parcole-George, I should have cited their paper here, showed that in fact, there's what you'd call Planckian scaling today. So that the Green's function is some anomalous power law, not so different from the kind of power laws that Dan was showing yesterday. And furthermore, there's this omega over t scaling, which Dan was also showing. Of course, I wouldn't immediately jump and fit this to his data. This is a toy model, but it's great to have a model that has exactly those generic properties. So he was writing on F in the self energy is square root of omega squared plus t squared, but that's a special case of this function. Okay, and in this case, for this model, we know this function exactly. We know the exact solution that was obtained by Parcole and George. And what's remarkable about it is that, the frequency, the natural frequency scale is just determined by the temperature, and it's entirely independent of U. So the only energy scale here in the microscopic problem, let's say the density is 1/2, so mu is also fixed to 0, then is U. But so if you're doing Boltzmann theory, if you're looking at some scattering rate or lifetime of a particle, in Boltzmann theory, or by Fermi's golden rule, it's always matrix element squared times some density of states. So, and the matrix element squared is some U to some power. That disappears. And this is a dissipative function here, and the dissipation is universal. It's independent of any coupling. It's just determined by Planck's constant. That's so we call it Planckian dissipation. Yeah. Right. So the U is the prefactor here. Yeah, dimensional analysis has to work out. So G has certain dimension that is not the dimension of temperature, and so you have to put it in to make that work out.
That because your that distribution that you choose that make like this.
Yeah, well, that's the big question, of course. How generic is this? I think, yeah. So here you don't have, U can be anything. So it's a whole phase where you got Planckian scaling. And it's much harder. In clean systems, you generally maybe have to tune a parameter to see the critical point. Not all, but many cases. Yeah, but here, right. The other one point I should make is that this is strongly self-averaging. The randomness, the Green's function just self-averages everywhere because this kind of self-averaging over the many-body space, which is 2 to the n possible random states here. So, yeah, okay.
And the physical dimension.
I mean, I think, so from the, when people are applying to black holes, where's the randomness? So I think this is something that Marla contributed, that what's really key is many-body chaos. This is a very strongly chaotic system. And so when you have a very strongly chaotic system, randomness is a very useful tool to understand its properties. I mean, we already knew that in condensed matter physics, where you use random matrix theory to study quantum chaos in the billiards and so on. So this is like a that same idea in steroids for a many-body system. Okay, so now, yeah, I guess I'm only going to get this far. Let's go to the density of states. Now here, I don't have any single particle basis. I just have to diagonalize this matrix. So this was done by Grisha Tanopolsky on 16 sites or something. You get, now it's a much harder problem. You're not diagonalizing a 16 by 16 matrix, you're diagonalizing a 2 to the 16 by 2 to the 16 matrix. And you just plot all the energy levels. So you look at the density of states, and you can see it looks very different. Okay, very different from that. This had this long tail. That's completely gone. Now, first, let's look at what happens when the energy is extensive, and then we look at the bottom of the band. So when you look at when the energy is extensive, well, again, by Boltzmann, it should be E to the entropy. But when you compute this entropy in the extensive limit, you get the same expression. Let's look at it in temperature. You get the same expression that you get for the random matrix theory, except there's a constant, S0. So this system has a 0 temperature entropy. At least, you notice this is when the system is extensive. I mean, taking the thermodynamic limit first, n has gone to infinity, and then you send the temperature to 0. Then you get this constant S0, which is actually a universal number, only depends on the filling, just computed. Okay. So this is, for us, this was a big shock. We've never seen anything like this before in condensed matter. Well, there's something called the ice model of Pauling, which has 0 temperature entropy. But that's really a ground state entropy, meaning that it's a finely tuned model whose ground state is exponentially degenerate, different dimer packings or something. But so that's a system which has a 0 temperature entropy due to a huge ground state degeneracy. Here, there is no huge ground state degeneration. We don't expect, it's a random system. Why should there be a degenerate ground state? Exponentially strong, especially when the system is gapless. So anyway, it's correct. And so this is really the first system to have a 0 temperature entropy without a ground state degeneracy. Yeah.
So if you take it to the other limit, you get 0.
Yeah, so that's what these plots show. I'm coming to that. Yeah.
Slope is a universal number.
It depends on the filling, nothing else. So this is the number for half filling.
But does it depend on the distribution?
No, it depends on the Q. So if you take a SYK 6 model with 6 fermion interaction, it's a different number. It's a different number for every Q. It's like some universal amplitude. Yeah.
Symmetries.
Symmetries, well, I mean, this is Majorana versus, yeah, so the Majorana one is half as large as the U1 complex one. That's about it. Filling is just the density of particles, that's Q. It goes from 0 to 1. Yeah. Yeah, actually I said it here, yeah. It's just yeah. It goes between 0 and 1. So half is the easiest point to solve. At half, it's just very simply related to the Majorana version. Okay, but actually there was another big literature which I was totally unaware of at that time, where people had been talking about 0 temperature entropies, and that was Hawking's theory of charged black holes. And so now that theory today has evolved a long way, where this kind of exactly solvable model has played a big role. So, in fact, so now let me come to Leo's point. So let's just look at the density of states down to 0 energy. So it's not so clear here, but it turns out if you do the numerics and also the analytics, the density of states, remember in the other model, it was order e to the n here and became order n here. Here it remains of order e to the n, but there's a prefactor that vanishes. And and this is the same S naught that still survives. And so these levels are exponentially dense down to the ground. So there's no degeneracy, but they're exponentially dense. And that tells you there is no quasi-particle basis. Because if you had some kind of quasi-particle, or some finite set of quasi-particles, there'd probably be n of those, n possible labels for those quasi-particles. So the total number of states will be of order n. The density of states cannot be exponentially large if there's a quasi-particle basis. So that is the proof that these states, you can't think of them as adding and removing a quasi-particle. They're just truly chaotic. They're just different wave functions, all of these states. They're totally different from each other. They just, the Hilbert space is 2 to the n dimensional, which is gigantic, and then many, many possible functions in there, which just happen to have energies really close to each other, all the way down to the ground. So there's nothing special about the ground state. So that's really the, okay. So in fact, a lot more is known. Like I said, we got this number S naught, but the full density of states, the crossover is known. And this comes from a theory of the Schwartzian due to, well, I don't know. Actually, this formula was first written down by Alex Ortland and collaborators in this matter, but a more complete derivation given by Baldacena, Witten, and others. Steve Schenker. All right, okay. And the same Cinch formula now also applies to actually black holes in 3 dimensions with a net charge. And we also understand why, but I don't have time for that. I don't even have time for condensed matter. Yeah.
So usually states near the ground state don't have like volume law entanglement. So these guys have volume law entanglement.
Well, everything's connected to everything. So there is no area law anywhere. That's not surprising. Yeah.
Ground state entropy is coming from.
No, I was very careful not to call it a ground state entropy. It's a 0 temperature entropy.
It's like in like microcanonical sense.
Yeah, these are the microcanonical states. Yes. Oh, it may have a twofold degeneracy with some global symmetries, but that's it. Yeah. Right. So normally, it's sufficient when you when you do Boltzmann stat mech, you take an energy window, say 1 over volume or 1 over n or something. That's enough. Even in a window of when your energy is extensive, even in a window of order 1 over n, you have exponentially many states. But here it turns out even down to the ground state, that's true here. That's not true at near 0 temperature in any system with quasi-particles. Yeah. I mean, this is the finite n spectrum. So if your temperature is smaller than e to the minus n, then it's not there. But the key point is the temperature has to be exponentially small for it to disappear, not temperature about a 1 over n. That's what happens in system with quasi-particle temperature e to the minus n.
All of that, then maybe
Yeah, well, this is where, these include exponentially small correction, not just 1 over n. Yeah. I think, so all these finite n corrections are extremely well understood in this, thanks to the work of the brilliant string theorists, and they're much less understood, strangely enough, for this problem. Yeah.
If I had to choose the n by 2 to the n random matrix,
Yeah.
what temperatures do I have to go down to?
Well, I mean, then, that's the same property as this. It's just that you've relabeled 2 to the, you just replace n by 2 to the n.
I guess are there important like universal differences in the levels of physics between random matrices and an SYK model with the same?
Right. So for example, here you get the Wigner-Dyson distributions. I believe these are also but I don't think it's really been proven. that the district level spacings here is also Wigner-Dyson.
And is there anything universal to the edge?
Yes, that's and that's entirely different in this model. Yeah, right. In fact, the whole Schwarzschild theory is a theory of the edge. That doesn't appear in that case. I was going to say something. Yeah, so the thing is, this gives you the number of variables here, however, is much smaller than the number of random variables in the model you suggested. Yeah.
Sorry, just to understand what you mean when you say the wave functions are changing chaotically, you're saying they're changing randomly but continuously in some sense?
No, so let's take a Fermi liquid, even an interacting Fermi liquid, with randomness, without randomness. And you say you know the ground state, it's a complicated wave function. And you want to know something about the excited state. Well, what we know, what is the statement that is quasi-particle? It means that you take a particle from here, and you move it there, and there's lots of readjustments in the neighborhood of where you move the particle. But the rest of the all the other particles really far away don't change at all. So the change from one state to the next is rather small. It's only adding and removing particles or quasi-particles here and there. Here, everything changes. All the particles are different between one state and the next. That's what I meant by chaos. Yeah.
Zero temperature entropy as signature of non-quasi particles?
For this model, yes. But it's sufficient, but not necessary. Because in finite dimensions, we don't have zero temperature entropy. So it's just for zero dimensions, things become simple and solvable. And the distinction is so clear. That's why you can prove such things. In higher dimensions, it's complicated. Yeah.
It's never possible to get this? Or?
In finite dimensions, the zero temperature entropy is always zero, yeah, for any model. But there's changes in the distribution and various conjectures of that in some paper. Okay, I think I'm out of time. So let's see. Yeah, we've been applying this to various, let me just mention, but I can't. So there's various finite dimensional extensions of this. Yeah, let me just show at least this. Yeah, so there's in some of these SYK models, this is optical conductivity data of Michon et al. As a function of frequency and temperature and the cuprates. And this kind of model just extended to finite dimensions with some realistic spatial modulations for some quantum critical point, including FL star to FL. We get almost exactly the same behavior with the same types of scaling. And we're hoping we can do such things for Dan's data, but let's see. All right, thank you.
Questions? Go ahead.
The function f? Yeah, well, we know it. It's some ratio of gamma functions in this case. No. So even in all cases, it's quite non. Right. Okay. Yeah. I think I see what you're saying. Right. So this thing is, when omega is 0, it's 1 over square root of temperature. When omega goes to infinity, it's 1 over square root of frequency. And there's some crossover between them. Right. So for example, when Dan yesterday wrote down, he wrote down sigma of omega, and T was, he said, it's omega squared plus T squared with some constant here, all to the 1/2. Now you can also write this as T to some constant alpha. You can write this as T to the 2 alpha times some function of omega over T. And in this case, the function is just square root of x squared plus a squared or something. F of x. Okay. I'm sorry. You can see down here. What Dan wrote down was some simple ansatz for this for the frequency and temperature dependence. And that meant the function f was just some simple thing like that. Sorry. It's not as simple here. So that function just depends on precisely the type of, it's a universal function independent of many details, but it's different for different universality. It certainly would be different in finite dimensions. And the data I was just showing you for the optical conductivity, there we are precisely fitting the function that we compute with the function that's observed. And it's different from the SYK, of course. Yeah. Well, I don't know. I mean, there's no space, so I don't even know how to talk about electromagnetic field here. But we can talk about that in the two-dimensional models. We have, in fact, I was showing you results for the conduct. People have studied nonlinear response also. And right now we've been working very hard in finite dimensions on the Hall coefficient. Hopefully we'll have a paper on that. Malian and Davide Valentines. Yeah.
Where does the disorder come from for the Toby case? Like, I mean, disorder in the interactions.
Yeah, excellent
How
point.
do you explain
Can I? Well, first of all, every cuprate has, dopant disorder. Secondly, when you look at STM data, even in the best crystals, there's always these gap maps are extremely disordered. So it's just an experimental fact that these are disordered systems. And then at the very end of things I didn't talk about, I was going to talk about even something more. No, what happened there? Yeah, so the actual data for strange metals has this famous foot here. And there's a lot of indication from many different directions that this cannot be there without disorder. So experimentally, the disorder is always there. I think even Steve Kivelson probably also talked about this disorder on the overdosed side. So then where did it come from? Well, is it just because of impurities? Yes, but there could also be that somehow strong interactions enhance the effect of disorder. Maybe there's some instabilities to various charge density wave states. And even with just a little disorder, all of those charge densities get pinned. And so then the electrons see quite a random environment. Yeah. But I mean, I would say from the experimental data and the cuprates anyway, the role of disorder is extremely clear. And once we do theories with even moderate disorder, we immediately start explaining the data. Whereas theories with zero disorder completely fail. But where it's ultimately coming from, I think that's an interesting open question. Yeah. Yeah.
Like, in our previous experience, the SYK benefit is that you have a simple self-energy distribution, but like you're also showing this like chaotic spectrum or something. So I wonder, like, the general study of the superconductor, like, is this like is like this chaotic structure general for any like zero-dimensional order, or like requires something to act like a that is let's say not a randomness model, like less tractable, but does it give you similar resistivity behavior?
Well, I would say that chaos is one of the way of well, that's what chaos is. Because once you don't have quasi-particles, then you cannot, I mean, this feature that successive energy levels are not related to each other still holds. And it's just that in zero dimensions, you can make a lot of progress in understanding such things. Understanding chaos in general in finite dimension is still a very open question, research question many people are thinking about. It's good, I mean, conceptually, but when people are using all these chaos diagnostics, talking about things that are essentially impossible to measure. So, I try to focus on things that can be measured in the near term or have already been measured. There's no shortage of measurement in the cuprates that need explanation.
Okay, with this, let's thank lecturer again.